Very good afternoon, everyone. Hope that you all are doing great. I am Nikki Rani, student of the NorthCap University, Gurugram. I will be the moderator for today's webinar on behalf of IEEE Women in Engineering. Remote sensing is a method by which we can detect physical characteristics of anything. So you now know that our topic for today's webinar is related to remote sensing. Well, that's right. Today's topic for the webinar is remote sensing of atmosphere, case study during recent COVID-19 lockdown period by Dr. D.V. Mahalakshmi ma'am and Lakshmi Kanchana ma'am. Our first speaker, Dr. D.V. Mahalakshmi ma'am, is a scientist who is awarded in Ph.D. in Meteorology and Oceanography. Dr. D.V. Mahalakshmi ma'am has specialization in atmosphere sciences and radiations and greenhouse gases. Our second speaker, Dr. Lakshmi Kanchana ma'am, have area specialization in atmospheric pollution, aerosol chemistry, and air pollution studies. Our speakers had written journals on the topics ozone variability influenced by its precursors and meteorological parameters, assessment of total columnar ozone climatology trends, and over the Indian subcontinent, and many more. Thank you to all the attendees for joining us today. If you have any queries, please write them down in the chat box. We will tick them up in the end. And for the feedback form, you will get the link in the description box. Now, without any further delay, I would like to invite our speakers to carry on from here to start our astounding webinar.
Can I start, ma'am? Can I start?
Yes, ma'am.
Hello?
You can start. Yes, ma'am.
Am I audible? Can I start?
Yes, ma'am. Yes, ma'am.
Today we are going to learn some basics about Earth atmosphere, so that what is the necessity of studying Earth atmosphere by using remote sensing data as well as some ground-based data, and also by using modeling. Before going to use remote sensing data or ground data or model, what is the cause behind it, why we have to study this atmosphere, we are going to see for about few slides. Then we'll start what is how we are studying and all. So as we know, atmosphere is divided into different layers, starting from the earth surface to the lowest part of the atmosphere up to 10 to 16 kilometer, we call it as troposphere. So the atmosphere is comprised of layers based on temperature. Why not with pressure and density? Since pressure and density both are exponentially decreasing, as shown here, from the earth surface to the top of the atmosphere, exponentially decreasing. So we cannot study with air pressure or air density. Thus, atmospheric scientists started studying atmosphere based on the temperature, because it is varying with height. How it is varying? So the atmosphere is based on this temperature, atmosphere is comprised of different layers, especially troposphere, stratosphere, mesosphere, and thermosphere. The lowest part of the atmosphere, the part we live, is called troposphere. See here, I have marked as this is a troposphere. Here also from the earth surface, if you see, near the atmosphere is divided into latitudes and longitudes. The 0 degrees latitude is called equator. At equator, what is the tropopause height? And at poles, what is the tropopause height? Because this troposphere varies with season as well as latitude wise. So before going to see seasonal wise, if you see latitude wise, the tropopause height is highest at the equator, because it is directly linked with the sun's radiation. The sun radiation directly falls at the equator, whereas the oblique rays will fall near the poles, because this is the main source causing convection and buoyancy force near the surface, which is is the main cause for the height of the tropopause height, estimating the tropopause height. So since more energy is available at the equator, we will have tropopause height of about 12 to 16 kilometers near the equator, whereas at poles it is only of 6 to 8 kilometers. However, in summer, the highest tropopause height will be appear either in the either at the equator or at the poles. And when coming to different layers of the atmosphere, if I describe more about the troposphere, it contains most of weather in the troposphere, such as clouds, rain, and snow, because which is directly influenced by the Earth's surface. Because most of the energy for the atmosphere also starts from the lowest part of the Earth's surface. Thus, most of the things will happen. 90% of the whatever atmosphere we'll see will be within the troposphere. And troposphere contains about 75% of the all of the air in the atmosphere, and also as well as almost all of the water vapor. This water can be in the form of three phases: water, liquid, and vapor phase. So because of that, the clouds, whatever we see, those mostly within the troposphere, since most of the water vapor present in the troposphere. And also, which is a greenhouse gas. This water vapor is a greenhouse gas, which is going to explain in details in next section. But however, it varies very dynamically, and thus studying about this greenhouse effect is very complex. And further thing, if any parcel of the air moves upwards, it expands. When air expands, it cools. Thus, in the troposphere, the temperature decreases with height. That we call it as lapse rate. In general, this lapse rate is in the lowest atmosphere 6.5 kilometers, 6.5 degrees centigrade per kilometer. However, due to ozone presence in the stratosphere, the temperature, instead of decreasing, temperature increases with height in the stratosphere because of the presence of ozone. Because this ozone absorbs high energy UV radiation. UV radiation is divided into three parts from UVA, UVB, and UVC. Except one UVC range, rest of the things will be absorbed in the stratosphere. Thus, we can see this is the only reason the temperature increases with height in the stratosphere. If you come to mesosphere, again temperature decreases with height up to 80 kilometers. We can see minus 90 degrees centigrade at tropopause height. And then again temperature increases with height in the thermosphere, because this thermosphere is directly influenced by the sun's energy. High energetic UV and X-ray radiation from the sun will be absorbed in the thermosphere, and high energetic solar radiation knocks electrons off molecules and atoms, turning them into ions with positive charge, causing thermosphere more heat than any other layers in the atmosphere. So this is all about the layers of the atmosphere. Now, if you see in the troposphere or anywhere, the composition of the air is a mixture of gases. If you see, nitrogen will be 78%, it will be occupied, and oxygen will be almost 21%. But rest of the gases, though they are 1%, they are of scientific interest because of they are helping in greenhouse warming due to human influence, that we are going to see in later sections. If you see dry air versus moist air, which is more mass with respect to this, you can see here same unit volume of air. If you take dry air, contains only oxygen and nitrogen and 1% of other gases. If you see molecular weight, it will be if you add all the things, only 28.9. If you see moist air, in the same unit volume of dry air, it will be replaced by moist air, that is water vapor is coming into picture, which is of molecular weight of only 18. So the net weight will be very less. So this is the difference between the dry air and moist air. However, we know that atmosphere is abundant with respect to N2 and O2 is concerned, and rest of the things are very 1%. So those we call it as trace gases. Among trace gases, few are greenhouse gases. Those are very important to us because they are causing our atmosphere is more warming than pre-industrial era, that we are going to see in later sections. If you see tropospheric ozone versus the stratospheric ozone, tropospheric ozone is helping us to absorb UV radiation, so that it is not allowing that UV radiation to travel into troposphere. If it is travels, it will be like more harmful to the humans. That way it is protecting us from this harmful UV radiation. So we call it as stratospheric ozone, we call it as good ozone. However, in stratospheric tropospheric ozone, we call it as which is a greenhouse gas, because it is forming due to all chemical reactions happening over the troposphere. As it is we can see day-to-day life our smog, which is because of this tropospheric ozone. This tropospheric, the radiation, the gases which we are calling as greenhouse gases, because they absorb radiation in the range of thermal radiation 9 to 10 micrometers range. Thus we call it as greenhouse gases. So if you see natural greenhouse gas versus human induced greenhouse gases, earlier what we used to have some minimum amount of greenhouse gases in the atmosphere that are emitted by naturally. So sun's radiation is emitting to the earth surface, and earth is absorbing that radiation and re-emitting that radiation. Due to the molecular or presence of greenhouse gases, they are re-emitting that gases, and few more heat is escaping to the space. So because of this, we can see only temperature as we feel comfortable temperature. Otherwise it would be cooler temperature. So minimum natural greenhouse effect is necessary for the comfort of human life or any other livings. However, nowadays, due to our human induced greenhouse gases day by day is increasing like anything, because of transport or deforestation and all, which are going to see in later sections, or you might be knowing of it. Because of that, more abundance of these gases leading to more absorption and making our earth atmosphere more warmer than what we see in preceding years. So day by day is increasing. If we coming to see whether among CO2, CH4, N2 and water vapor, which is more highly scientific concern is CO2, it is not because of it is more global greenhouse gases. It is only because of that abundance of CO2 is more in the atmosphere compared to other gases. If you see CO2 concentration in the atmosphere is approximately 380 ppm. However, if you see methane, it is only 1.75 ppm. So compared to quantity of this is very less. CH4 quantity is very less in the atmosphere. Thus, we are not getting more warming because of CH4. So CO2 is major concern because of only its abundance, but not the effect. If you see the effect, compared to carbon dioxide, methane is more complicated warming effect than CO2. 25% it will be more. If you see here, I can categorically mention carbon dioxide is 76%. It is contributing for global warming. Methane is 16%. Nitrous oxide is only 6%. Other gases are 2%. So otherwise, nitrous oxide will be effective 300 times more than the CO2. Other gases are affect more 1,000 times than the carbon dioxide, but their abundance in the atmosphere is very less. Thus, CO2 is major. Mostly people were studying about CO2. Otherwise, water vapor is also very important, but it is highly dynamic, where we cannot, it is very tough to measure their concentrations at particular time and space. So here, if you see the radiative forcing, this zero is like zero radiative forcing. If it is negative side, the atmosphere will be cool. If it is positive side, atmosphere will be warming. So aerosols and all will be helping for the surface cooling. Even stratospheric ozone also helping for the surface cooling or atmospheric normal temperatures. However, human influenced CO2, other greenhouse gases, as well as tropospheric ozone and anthropogenic effect. See, I have marked here with here all total anthropogenic effect is contributing for more or less plus 2.5 watts per meter square. And coming to next, this is the energy. Sun's energy is coming to the earth surface. Some of the energy is absorbing at the earth surface. After absorbing earth, as per the Stefan's law, any energy above 0 degree
Ma'am, Devi Mahalakshmi, ma'am, from your screen stopped sharing.
since sun is at 6000 kelvin, it emits from radiation at maximum peak of, as per the Planck's law, 0.5 micrometer. However, earth is absorbing this radiation, and as per this temperature rate of 25 degrees
Excuse
centigrade,
me,
it
ma'am.
can emit at a maximum rate of 10 micrometers. So based on this, other greenhouse gases also absorbing it. So each gas will absorb at certain wavelengths. Those absorbing bands will give the information for the satellite sensors to study about it, where we can retrieve these gases concentration based on the absorption bands, because each will absorb at different bands. That is the basic information which we will have. Based on that, we can retrieve the those gases concentration. The overview of greenhouse gases in 2018 by the US, it was mentioned that carbon dioxide is 81% and methane is 10% and nitrous oxide is 7%. If you see each sector wise, transportation sector is emitting at contributing for 31% of the human influenced anthropogenic forces. Electricity is 37% and industrial activities are contributing for 15%, and residential and commercial are 10%, and other things are coming under coming at falling at 6%. So if you see also, this water vapor is although in troposphere 96% and carbon dioxide is 4%, rest are like very less. Methane is 0.002. There is a positive feedback though for the global warming. This we can simply explain like, if you take loan, that only principal amount will be there, but interest will be add on to that. So if you delay that principal, it will like feedback, interest will be component will be more like that. This human caused in greenhouse gases initially might be the less, but this feedback loop adds further more into, see here, leading to more anthropogenic effect and leading to more global warming. Thus, air pollutants now we can study by using based on the above information, based on the chemistry and emissions and meteorology. So we can see the emission scenario by using three things: either measurements, source appointment like isotopes and all, either by using modeling. So from the CO2, if you see growth rate from the 1985 onwards, from the pre-industrial era, we are seeing a growth rate of 0.2 ppm per year. In the similar way, CH4 also increasing. So if you see their concentration growth rate here from the 1985 to here, as per the these are all things I have taken it from the GAW program. And now we have seen the different things of how it is affecting. So now today I'm going to explain further details about how this remote sensing
Excuse me,
data
ma'am, your
is
screen is not visible.
right now, sir, or since long. Is it visible, sir?
No, ma'am. You have to share your screen again.
Okay.
Yes, ma'am. Now it's visible.
And now I'm going to show one example by using this remote sensing data. What we have done, small study we have carried out. So as we said, from the sun, radiation is reaching to the earth surface. So we wanted to see how much surface radiation is reaching to the sun, reaching to the earth surface from the sun. So for that, what we have used is different satellite data we have used to retrieve this surface net radiation. So some of the radiation products from the satellites is directly available. That is from ISCCP, which is providing at 3 hourly at 2.5 degrees spatial resolution, and second one is SRP product at 3 hourly resolution at temporal resolution with a spatial resolution of 1 degree global wise. So these four are different satellite products available for estimating surface net radiation. What we made is one more attempt we have made, because these spatial resolutions which are not useful for the models to use. So we made an attempt by using different satellite products, basic products, and try to estimate this net surface radiation at 5 kilometers resolution, at 5 kilometers spatial resolution, and every half an hour temporal resolution. That I am going to share present now. We have different methods to estimate this net radiation, such as parameterization scheme, statistical regression approaches, and machine learning algorithms. At present, I am going to show parameterization scheme, what we have used and how we have estimated. To use this parameterization scheme, I have used different products as listed here from the source of from the MODIS satellites at available at resolution as shown here. For example, air temperature from MODIS product, which is available at 5 km by 5 km resolution, and dew point temperature from the same product, which is also available at 5 km by 5 km, and land surface temperature from the MODIS sensor, available from mod 11, available at 1 kilometer by 1 kilometer, and emissivity from the same product, and albedo from different MODIS product, MODIS 43, and solar zenith angle from mod 03 product, which are all available at these resolutions. And we have flux tower, which is installed at Sundarban, as shown here. This yellow color dot, Sundarban is a different ecosystem. The data is used for validating this product. See, this is a ground-based satellite tower equipped with different sensors at different altitude, as shown here. This is, we call it as eddy flux tower, which is installed at Boni Camp. The tower height is some 30 meters something, according to that this equation given by in the literature. 2h tan 81 gives footprint of 200 meters. So whatever readings will get it from this flux tower will be applicable within 200 meters footprint limit. So this is our methodology followed in that study. We have extracted air temperature and dew point temperature from the MODIS satellite data, and by using Passage-Clapeyron equation, we have estimated surface vapor pressure, and by using again solar zenith angle, we have computed incoming surface shortwave radiation in terms of watts per meter square. Then we have used albedo product in order to estimate outgoing surface shortwave radiation. Then ultimately, what we have is incoming shortwave and outgoing surface shortwave. So we have NSSR means net surface solar radiation in terms of watts per meter square. Similarly, other channel we have used land surface temperature and land surface emissivity. According to Stefan's law, we have estimated outgoing surface long wave radiation And we have also used air emissivity from the same from the equations which are available in literature, and accordingly we have computed incoming surface long wave radiation. So we have incoming long wave radiation, outgoing long wave radiation at the surface, so we can able to estimate net surface long wave radiation, and details are explained in the different slides. These are like what are equations I have used for this shortwave computation. S naught cos square theta by d. T is computed as shown here, which is only input by E naught. E naught is, as I said, already computed by using Clausius-Clapeyron equation as shown here. This is entire methodology is nothing but Gilsman's 1972 parameterization, which we have used it for computing net shortwave radiation. Similarly, Prata 1996 parameterization scheme is used to estimate net long wave radiation by using the product of MODIS as shown here. This E naught is as shown earlier, the equation Clausius-Clapeyron. Then we have estimated zeta, which is from that we have estimated air emissivity. So I have air emissivity and air temperature, so we can easily compute Stefan's law. Long wave in and long wave out also computed as shown here. Long wave out we have only taken from all 11 product, where it gives land surface temperature and land emissivity. Land emissivity calculated as at 31 band and 32 band mean. We have considered as a surface emissivity. So now we have net shortwave radiation as well as net long wave radiation. So we can easily compute net radiation available at the surface. So these are the list of products available from the MODIS sensor, in which the highlighted things are used in the present study. See, this is the albedo product, this is atmospheric profiles. So mod 07 doesn't give a temperature or dew point temperature. However, by using at surface level at 1000 HPA, we consider as a temperature that is near to the earth surface. So this study is only carried out during clear sky days. So either that study area is clear sky day or cloudy day is decided based on the other product, which is used as an ancillary product, MODIS cloud fraction, that is mod 06_L2. These red things are like cloudy days. So this study is carried out from November to March. These red dates from 1 to 30, this red color indicate cloudy day, whereas clear sky days is yellow color things are clear sky day. I think it is in 2012 we have carried out this study. So though MODIS sensor gives at overpass time of 10:30 or nearly 10:30 a.m. and 1:30 p.m., but we need the diurnal variation of net radiation from this one point. So for that we have used sinusoidal model, and we try to compute the diurnal variation of this net radiation by using sinusoidal model as shown here. Then we have compared this estimated net surface radiation or individual components of shortwave in, shortwave out, and long wave in and long wave out with the flux tower as discussed or as shown earlier, and we got very good results as shown here. R square or within the acceptable limit as discussed in the literatures. So at last we could be able to estimate these are the statistics out of that validation, and this is the shortwave incoming from the remote sensing data and shortwave outgoing from the remote sensing data spatially at high resolution, that is at 5 kilometers by 5 kilometers, which are very useful for modeling. Some of the soil modelings are very this net radiation is very input to those models. So this is how long wave radiation is varying. Downward long wave radiation from November 2012 to March 2000. This is my study period: November 2012, December 2012, and Jan, February. 5 months I have seen daily. This is daily average net radiation after using that sinusoidal model. So this is the mean peak of November 2012. This is mean peak of December, January, February, and so on. March, and this is a scale for that, in terms of watts per meter square. And further, what we did is, since land use land cover over Indian region is very dynamic, and it is not unique as we see generally in US and all. So we have taken different categories of land use land cover parts, and we try to see how this energy is varying, like forest, agriculture, water, and urban area, forest plus water area. So what we found is the incoming radiation, which is not varying that much with these land use land covers types, because it is nothing to do with at surface or the atmosphere. It is directly coming from the atmosphere, from the sun to the surface through atmosphere. However, these outgoing components, either short wave or long wave, is influenced by this type, like either agriculture, forest, or so it is highly varying, that we can able to see what how much which is emitting more and which is emitting less. So incoming also, see, long wave incoming is not that much varied as per the different categories of land use land cover. However, long wave out is varied, highly varied with this categories. The conclusions is this model is able to estimate this all four components of the net radiation, and validated again this different regions, and shortwave incoming and shortwave long wave incoming are not shown much variation with different ecosystems. However, outgoings are shortwave outgoing and long wave outgoings are shown variations among different ecosystems. As earlier I said, three different methods are there. One is parameterization schemes and neural networks. Now I am going to show how this neural network is able to estimate this net radiation. So we have used basic ANN network as shown here, with three inputs and with different hidden layers, and output is net surface radiation. For that, our flux tower data, as I shown, our Sundarban region of West Bengal in Kolkata is divided into three different data sets: training data set, validating the data set, and testing the data set. For training purpose, I think 70% of the data is used, rest 30% is used for validating and testing the model. So what we have used algorithm is as shown here, Mark Quadit Levenberg algorithm is used, and we have computed some statistical, and we have compared with the ground-based measurements, how our model is able to capturing this estimated net surface radiation and all. So we have seen different ANN scenarios by using all four inputs of the that I am going to show what are the inputs I have used. And by using all inputs for the model, how ANN is captured with respect to observed net surface radiation, and by eliminating one parameter from this, how it is trying to estimate. I might be taken here four input parameters, but in this I think I have second one is here I have used only by eliminating one first parameter. Then this is for eliminating second parameter, but rest all same. This is for eliminating third input parameter, but rest all I have used. So which is giving best and which is really dependent on either estimating or computing this net radiation or not. So I have a see, and separate study also I have carried out, how model is able to capture during clear sky day versus cloudy day. If you see here, statistics model is able to capture in a better manner than cloud during clear sky days compared to cloudy sky day. So RMS error is half of is reduced during clear sky days. So this cloudy and clear sky days also, I have categorized the data based on the net surface radiation. If I see net radiation is in the sinusoidal model, I have declared it as a clear sky day. And if it is like zigzag, then we consider this as a cloudy sky day. So our study area is divided into clear sky day and cloudy day based on this assumption, or based on this method. Then we have estimated ANN model of 4 different ANN models were used to estimate, and which is giving best we have analyzed. See, what are input parameters I have taken is temperature, wind speed, relative humidity, and wind direction are the input to the model. ANN can train the model with no need of dependent parameters. It can be of independent parameters. So these are all, I can say, except temperature and up to somewhat in RH. These not much related to with the net radiation part. But however, we have used these input parameters to the model, and we could be able to see November 2012, our red color indicates ANN estimated net radiation, blue color indicates observed. It is exactly matching with the observations during in November, in December, as well as in January. Each peak corresponding to one day, since radiation vary in sinusoidal model, so each sine curve belongs to each day. So as we know, incoming radiation somewhat is related to net radiation. So we have used one linear model by empirical relation between estimated incoming shortwave radiation and versus net radiation. We try to estimate regression relation here shown here, and then by using we have estimated, and it gave good results than the ANN, because it is direct dependent parameter which we have used here. But if you see overall India, we may be having good network of air temperature, relative humidity, wind speed, and wind direction data rather than this net radiation. We don't have that much data availability of incoming like GSR, global solar radiation, compared to the air temperature and all basic weather parameters. So though this linear model gives accurate results, but getting GSR data availability over India is very limited. So we have to dependent on these ANN models because of this. As I said earlier, one parameters excluded. ANN 1 model indicating when we have excluded air temperature, ANN 2 indicating when we have excluded relative humidity, but rest parameters are considered as input like air temperature, wind speed, and wind direction. ANN all indicates all the parameters like air temperature, relative humidity, wind speed, and wind direction. That way, which is giving more appropriate results, we try to see by using different statistical computations. First one is like ultimately no doubt about it, it is linear model because it is directly dependent parameter of solar radiation. The second one is, if you see when I have excluded wind direction, which is may not be that much dependent on estimating radiation component. So when we have excluded wind direction, our results are shown high compared to rest of the ANN models. So the significance dependent variable parameter on estimated value, we have seen some statistical feature selection method which is highly depending on all. We try to see, then based on that which parameters is influencing we have seen, and based on that ANN estimated, we can see these are the estimated spatial maps of this net radiation by using ANN for the Julian days, like January 10th. This is like January 28th. Maybe 38th Julian day means maybe it falls in the February, and 51 day of 2013 means it may be of March month. So some selected days I have shown here. The ANN model is giving RMS error of 64 watts per meter square with a R square value of 0.75. So this is how this remote sensing data is very how it is really helpful to estimating different parameters. And as our today talk is about remote sensing data with respect to COVID-19, my friend is going to take over now on basic results of this COVID-19 time, how these air pollutants are changed. However, here I'm going to show only AOD part. during 1st to 21st March of 2020. This is modest derived AOD over Indian region, as scale mentioned here. You can see during pre-COVID period, high amount of AOD is available, which is proxy for air pollution. At IGP region or some other parts of the Indian region is shown highest values. But however, during if you coming to next week wise, during lockdown pages, atmosphere is mostly clear during the up to 15th April, or even till April end. If you see even climatological mean from 2009 to 19, climatology of April, we have seen highest AOD values over IGP region and here Bangladesh and all. But however, this is not the scenario of during lockdown. So my friend now going to take this, going to explain in further sections how other air pollutants like NO2 and all, how they vary. Thank you one and all for bearing me till now. Madam. Hello. Am I audible?
Yes, ma'am.
Kanchana. Mine is over, sir. Sir, now Lakshmi Kanchana will take over of this presentation.
Okay, ma'am. Ma'am, please share your screen if you want to.
Okay.
Lakshmi, ma'am, you are on mute. Please. Yes, ma'am. You can start now. Ma'am, your voice is a little bit lower. Can you please bring your microphone to your near to your mouth?
Yes, sir. Am I audible, sir?
Yes, ma'am.
Can I start, sir?
Yes, ma'am.
Good afternoon, one and all. I am Kanchana, working in the NRSC ISRO. So today I'll be talking about case study during recent COVID-19 lockdown period. So first coming, what is Air pollution. So air pollution is nothing but it refers to the release of some harmful contaminants like any chemicals, toxic gases into the Earth's atmosphere. So these contaminants, they are very harmful and also pose serious health issues. And some causes that contribute to this air pollution are mining operations, the burning of fossil fuels. For example, these release huge amounts of gases. For example, carbon monoxide, nitrogen oxide, sulfur dioxide. So these are nothing but harmful, and also they are their threat also to the climate change. And next, that is nothing but the burning of fossil fuels and also the exhaust gases of some from industries and factories. So these industries, factories, they release these harmful gases. So for example, if we can see in this photograph here, there's an air pollution from an industrial source. For example, power plants. So power plants mainly they emit sulfur dioxide. So these effects of this air pollution, they vary based on the kind of pollutant also, but generally the health impact of this, they increased risk of respiratory illness, cardiovascular problems, the skin diseases, skin cancer, and also the global warming, the ozone depletion, and hazards to wildlife. So next, coming to what are air pollutants. So we have seen what is air pollution, and next coming to what are air pollutants. So pollutants are nothing but these either solid, liquids, or gases, and these are sufficient enough in concentrations which cause the threat to the people and also to the animals, vegetation, etc. So these come from both the natural sources and also the human activities. So human activities are nothing but the industrial complexes, the power plants, mobile vehicles, ships, aircraft, and etc. I mean, natural sources are nothing but the burning. I mean, fossil bio forest fires burning, that you can call it as natural source. And human activities are nothing but these power plants, industrial complexes, the motor vehicles, etc. And next, coming to what are the primary and secondary pollutants. So primary pollutant is nothing but just an emitted directly. It's a pollutant emitted from a source directly into the atmosphere. So one example, the volcanic eruptions, the factories. So you can call them as primary pollutants. For example, carbon monoxide, nitrogen oxides, all volatile organic compounds, particulate matter. So these are come under primary pollutants. So nitrogen oxides here, they are nothing but NO plus NO2. You can call as nitrogen oxides for in simple terms. NO is nothing but nitrogen monoxide, and NO2 is nothing but nitrogen dioxide. And sulfur oxide, you can call it as sulfur dioxide. And this is carbon monoxide, these volatile organic compounds. And particulate matter, these are nothing but particulate matter, you can tell it as PM10, PM2.5. They are nothing but diameter which are less than 10 micron. They are also harmful. I mean, they respiratory problems and all. PM2.5, PM10. PM2.5 is diameter less than nothing but 2.5 micron, and PM10 is nothing but a diameter having less than 10 micron. So they are, you can call them as primary pollutants. And secondary air pollutants are nothing but they form when a chemical reaction occurs between a primary pollutant and some other component of air. So we can call it as a secondary pollutant. For example, the ground level ozone and the smog. So they occur when a reaction occurs between a primary pollutant and some other component of air, that is water vapor or another pollutant. Primary is nothing but it's directly emitted from a source. Secondary occurs when a reaction occurs between a primary pollutant and some other component. You can call it a secondary pollutant. And some examples of secondary pollutants, you can take it as ground level ozone and nothing but the smog. So here you can nothing see but primary pollutants and the secondary pollutants here. So as you can see in this, the primary pollutants, nothing but I have told in the previous slide that carbon monoxide, sulfur dioxide, volatile organic compounds, NO plus NO2, we are calling it as NOx. So the sources were nothing but natural sources, the stationary sources, the transport, the rural, urban sources. For example, if you take NOx, mainly it comes from the transport, vehicular transport. You get one of the main source of NOx. And carbon monoxide also transport, the biomass burning, forest fire occurs. So most of them, when forest fires occurs, it releases huge amount of carbon monoxide. Power plants, if we take, they emit most of sulfur dioxide. So these are, you can call it as primary pollutants. That is directly they are emitted from the source. And secondary pollutants, when a reaction occurs between primary pollutant and some other pollutant, secondary pollutant formation. Secondary pollutants are formed. For example, acid rain. And if you take, for example, smog, ozone, these all are nothing but you can call it as secondary pollutant. So for ozone, you can call it as secondary pollutant because if it formation, if you take, it occurs in the presence of sunlight and its precursors. Precursors are nothing but they are used in the formation of ozone. For example, NOx, if you take, so NOx here I'm taking, here I'm considering it as NO plus NO2. You can call it as NOx, carbon monoxide, the organic compounds. So these are nothing but these, and in the presence of sunlight, ozone formation takes place. So that you are calling it as a secondary pollutant. And if you take next to take smog, as you all know, Delhi smog also will be much aware of that one. So smog is nothing but it's nothing but a combination of smoke and fog. So smog actually it has resulted from coal burning in an area caused by mixture of smoke and again sulfur dioxide. So nowadays vehicle emissions and industrial emissions, these are also acted on the atmosphere by ultraviolet light from the sun to form these secondary pollutants. So I've told us primary pollutants, for example, sulfur dioxide. If you take, so they are desirable. I mean, these measurements are highly important because they are important in the terms of air pollution, atmospheric chemistry, and also in terms of climate change. And these are some of the sources of SO2. For example, coal in the power plants. If you take industries, petroleum refineries, transport sector. So these are sources of SO2 and CO. Also, you can take it's an atmospheric trace gases. The trace gas it's present in very minute quantity, but it has a large impact on the climate change and all. So you can call it as CO. It is important atmospheric trace gases. And through its reaction with hydroxyl radical is nothing but OH you can call. So it affects the oxidizing capacity of the troposphere and is a precursor of ozone. Like these all CO and all, they're the precursor of ozone formation. So all these they aid in the formation of ozone. Troposphere is nothing but from the around 12 to 15 kilometers troposphere, you can call it as that one. So enhancement of this concentration, it not only affects the air quality, but is also a strong impact on regional weather and climate change. So CO, as you all know, it's a colorless gas, tasteless, poisonous gas, and it's a major air pollutant. And you can tell it's an indirect greenhouse gas having an adverse effect on humans and animals. It's not a direct greenhouse gas; it's an indirect greenhouse gas. You can tell it's a trace gas. And some of the sources of CO, you can tell the biofuel, the biomass burning, mainly from the forest fire. So the when forest fires happens, a major amount of gas that is nothing but carbon monoxide, and incomplete combustion of fossil fuel, that is gasoline vehicles, and oxidation of methane and other hydrocarbons. So these all are nothing but the sources of carbon monoxide. So this is and next one, like how I've told air pollution monitoring, how this monitoring takes place now. So we have seen what are the primary pollutants, what are the secondary pollutants, what is air pollution, what are the pollutants. So how this air pollution monitoring take place. So first is through the means of ground-based measurements. Like here we have can see the ground-based measurements here. So for example, we have the trace gas analyzers, the greenhouse gas analyzer, and the ethylometer. So trace gas analyzer are nothing but, for example, it just gives these are situated at a point location. So at that location, what are the concentration of the gases that we can come to know through trace gas analyzers. For example, ozone is a trace gas. NOx, when I'm telling NOx, it is NO plus NO2. Sulfur dioxide is SO2. Carbon monoxide. So these are nothing but the trace gases. Greenhouse gas is nothing but a carbon dioxide, methane, water vapor. So ethylometer is nothing but it gives a black carbon. So this is nothing but incomplete combustion of fossil fuel that happens at particulate matter. You can call it as a black carbon. So these are nothing but the ground-based measurements. So ground-based measurements are nothing but they are at a location and a concentration of that gases you get at a particular location. So when you come to next is nothing but satellite data. Satellite data it is advantages of this satellite data. Nothing but it gives more spatial coverage and so that your ground data is only at point location. So spatial satellite data, when you take it, gives only the spatial coverage. So you can better get a better idea of the process taking place. Satellite data, you have different instruments here. For example, the ozone monitoring instrument here, which gives nitrogen dioxide, that is NO2, ozone, it gives. And next is the Sentinel 5 tropospheric monitoring instrument. This is nothing but TROPOME. This gives NO2, it gives CO, it gives. And some they have some agencies like NASA is there, European Space Agency is there. Aura ozone monitoring instrument is from NASA. Sentinel 5 is from European Space Agencies. This for example NO2, Aura ozone monitoring instrument. Sentinel 5 tropospheric monitoring instrument, it gives carbon monoxide NO2 and measurement of pollution in the troposphere. This MOPIT, this onboard Terra. So this gives a tropospheric carbon monoxide, and you have different others like atmospheric infrared sounder. This also give the vertical profiles of carbon monoxide. This onboard aqua, and these are some tropospheric emission spectrometer onboard. These are some NASA's Earth observation system programs. And next you have infrared atmospheric sounding interferometer, EAC you can call it as onboard METOP. These onboard European space agencies. And the aerosol optical depth you have from models. These are the but also from the NASA. These are onboard the Terra and Aqua sensors. And so air pollution monitoring is mainly done through ground-based measurements. Second is satellite data. So these are the different sensors, different instrument on board different platforms you can call, both by NASA and European Space Agency. And this data is freely available through different sites. And next is the chemical transport models. Also, you can air pollution monitoring. You can simulate the concentrations and you can validate the models. So these are some of the parameters and some satellites here. For example, if you take the parameter NO2, nitrogen dioxide, these are different satellites which are giving NO2 and carbon monoxide. You have SO2, you have carbon dioxide, you have ozone, you have, and these are some resolutions. The what is the wavelength, what is the number of pass per day. Sorry, there's nothing but GOM. There's nothing but global ozone monitoring instrument. For example, red, for example, if you take, they are not currently operational, and blue, for example, if you take, they're currently operational. Data, if you can take that one. And EAC, atmospheric infrared sounding interferometer. CO2 is nothing but goes at satellite application just from Japan Space Agency. Like different sensors you have for getting the different parameters. These are nothing but the satellite based data. So this is one example of ground-based instruments for monitoring ozone, NOx, CO, and this is nothing but the rate of change of ozone. So first A here you can see this is nothing but the ozone, and B is nothing but the NOx, C is nothing but the carbon monoxide, and this is nothing but the rate of change of ozone. And here the different plots, colors you can see are the different seasons. So ozone, if you see here, so during daytime, there's maximum concentration of ozone because it occurs in the presence of sunlight and other precursors. So maximum formation of ozone takes takes place during afternoon hours, and minimum concentration is during morning and later evening hours. So as I've told, NOx and CO, they are the precursors for this ozone formation. That is, they are aid in the formation of ozone. Their concentration decreases during afternoon time. And these are the different seasons which are given here. For example, ozone, if you take, maximum concentration can be during pre-monsoon. So pre-monsoon, when I'm telling, it is March, April, May. Maximum amount of sunlight, and so there will be maximum amount of ozone formation. And it can also be in the time of winter due to boundary layer height and also long range transport. Like ozone formation at a particular site, if you take, it also can be transported from the other sites, also from the rural sites also it can be transported. So maximum concentration, it varies, that is seasonally it varies. It can be sometimes in pre-monsoon, it can be in winter, but monsoon it will be low concentration because of the rain. It will be, the pollutants will be washed off, and low concentration of ozone will generally be in the monsoon season. So next, coming to this COVID lockdown. So as you can see this one, so Delhi's air quality has improved remarkably during the shutdown process. As you can see from these figures, this is during lockdown, and when it is not in the lockdown process. So during lockdown, you can see how this is the how they are there, and so also you can see from Lucknow, which is one of the most populated cities and the financial capital, also the difference during lockdown and other general events. So, as part of this lockdown process, we have taken the satellite data, that is a tropospheric monitoring instrument, that is a Tropome, as I've showed earlier in my slides, from European Space Agency. And we have seen the concentrations during the pre-lockdown period. So, as I've told here, so government of India has announced a lockdown due to prevent the spread of COVID-19 in 4 phases. So as you can see here, 25th March to 14th April, we are taking as phase 1, 15th to the 3rd May as phase 2, 4th to 17th as phase 3, and 18th to 31st as phase 4. So this is the 1st March to 21st March of 20, and to 1st March to 21st March of 19. So this we are taking it as a pre-lockdown period, and 25th March to 14th April, as I've taken, you can taking it as phase 1 of lockdown. And so this is during the period 20, and this is during the period 2019. And this is the difference. You can see a color bar here, which is in molecules per centimeter square. And this is a tropospheric NO2 concentrations from NO2 concentrations from satellite data. And this is 25th March to 14th April of 20, and this is of 19. We are comparing 20 period phase 1 to same of 2019, and this is a difference map here, spatial map. So mainly NO2, if you can see here, the eastern region of India is mainly the hotspot consisting of power plants here. So when you take the pre-lockdown of years 2019, the extent of TCN hotspot regions, mainly the eastern and national capital region, they remain same. However, mild reduction during pre-lockdown of 20 was there compared to 2019. So when you take NO2, the major hotspot is nothing but the power plants. So power plants were operational during the lockdown period, but mild reduction was there when compared to 20 uh, in comparison to 2019. So we had this could be due to interannual variability in absence of the source locations due to lockdown imposed by neighboring countries, which is through long range transport. So other countries have imposed a lockdown prior to us. So the this difference when compared to 20 and 19, mild reduction was there during pre-lockdown of 20 when compared to 2019. So we are telling this could be due to lockdown imposed by neighboring countries. So when there were neighboring countries, they had previous dates of lockdown. So that could have influenced this concentrations of NO2 at at India. For example, lockdown at China was from much earlier, Italy, 21st February, Malaysia. So these could have caused the concentrations to be lesser. So as I've told, NO2, the major hotspot is nothing but the power plant. So mainly, if you can see this in the eastern region. So if you can see in my previous slide here, major hotspot of NO2 is nothing but the power plants, and these were operational during the lockdown process. So you can see here the eastern region of India. It has a significant number of power plants and refineries with associated industries. And phase 1 of lockdown, if you take, a reduction is observed, which is due to shutdown of industries and urban activities such as transport and small scale industries. And southern part of India reported less values during pre-lockdown phase 1. And if we tell the hotspots over southern part are not as dense as in the eastern, would be the reasons for its low values. If you take southern part, it could be because they are not much a hotspots region as come because the NO2, the major hotspots regions are in the eastern part of India and northeast also. Northeast mainly due to the biomass burning. So during lockdown, mild reduction was there because the power plants were operational, and as you know, transportation like everything was shut down during the phase 1, phase 2 of lockdown. Only some essential services like pharma and all some emergencies only were operational. So the difference we could see during this when we compare 2020 to 19. And hotspots or southern part of India are not as dense, which could be also when the Roberts values. The one more reason could be dispersion of these values as a result of land and sea breeze, since it's surrounded by Bay of Bengal and Arabian Sea over this region. Southern part, so their values were low, surrounded by land sea breeze effect. So that could also be the reason for giving low values in southern part of India. So these are some list of power plants and industries which are located in the eastern part of India. And as I've told, increase in this level over the northern region could be due to the seasonal biomass burning in this region. So as I've showed in my slide, it could be the biomass burning in this region. Northeast India is mainly due to the seasonal biomass burning in this region. And next coming to this carbon monoxide. So mainly when coming to NO2, so we have taken the pre-lockdown period, we have compared the 2020 to 19, and phase 1 we have compared, and phase 2 also we have compared. So since during a lockdown period, the industries like power plants were operational, we could see the effect of anthropogenic sources like any moment of some during phase 2 some restrictions were when some were allowed, like any some small scale industries were opened, and some agriculture burning was also opened during phase 2. So that effect we could see during this lockdown period. And next coming to this carbon monoxide. So this also using satellite data, we have done the analysis for pre-lockdown period, phase 1 of lockdown, and phase 2 of lockdown. This also is using this tropospheric monitoring instrument on board European Space Agency, where we have obtained the tropospheric carbon monoxide data. And increase of this TCC is nothing but the total carbon monoxide. So northeast region of India is mainly attributed to fire counts during the phase 1 of lockdown. So this A is nothing but the pre-lockdown, B is nothing but the phase 1 of lockdown. And next slide is nothing but the phase 2 of lockdown. And this is nothing but the fire counts which we have done the analysis for phase 1 and phase 2. So phase 2, there was a reduction in the northeast part of India, mainly because the fire counts were reduced. And phase 1, you can see more fire counts in northeast India. Here, this part you can see. And phase 1, you can see here little fire counts. I mean, the high concentrations of carbon monoxide. So during phase 1, IGP region, north and south region, they show decreased levels compared to same period of 2019. And these decreased levels are attributed to shutdown of industries, absence of transportation, and restriction on crop residue burning. But household emissions due to are still present, which is a major. But you can tell this household emissions are still present due to lockdown, which is a major contributor to CO. And next, this is my next slide here. So phase, except in northeast region, consistent increase is observed during phase 2. Enhancement in TCC levels is observed during phase 2, and you can take the phase 2 of lockdown also. Mainly fire activity was DCC levels are decreased, which is mainly attributed to fire activity in this region. That's also. Thank you from my side. Thank you, sir.
Nikki, you are not audible.
Yes, sir. Hello.
Thank you, ma'am. It's just Nikki is not audible right now.
Okay.
Yeah.
Sir, could you get me, sir? Could you get my presentation?
Yes, ma'am. It was it was good, ma'am. Very informative. Uh, just unmute yourself, Nikki. Nikki, you are not audible. at the end of the webinar. Uh, thank you, ma'am, for enlightening us with the knowledge of remote sensing of atmosphere. Now, now uh, I would like our audience to ask questions. And the yes, ma'am. Now, first question.
How you handle outliers? So this is the question now. What we got?
Yes, ma'am.
Sir, we'll try to see that first of all, we'll retrend the data. After retrending, and initially what we'll have is initial data. From there, any extremes like heat waves, droughts, or El Nino events. So we'll try to see in order to normalize those things before going for any further analysis. So we'll retrend the data, and so that it will come to see that actual variation of this. So that way, sometimes we'll try to eliminate these outliers and all. And also some statistical parameters we'll see. Based on that, we will try to eliminate outliers.
Okay, ma'am. I think we are done with our questions. Like it was only one. So thank you, DV Mahalakshmi ma'am and Lakshmi Kanchana ma'am, for your precious time. It is very informative and amazing webinar. And thank you to all of the attendees for joining us today. We hope that you all have learned something in this webinar, and we hope see you all to in upcoming webinars. Thank you all.
Thank you, sir.
Thank you, sir.
Thank you,
Thank you.
sir.
Thank you.